Hello class, welcome to today's lesson, which is subtopic 3.6, applications of trigonometry. Some classic applications of trigonometry. Okay, let's start. First, I need to define what the angle of elevation and the angle of depression are. What are these two things? These are very common in regards to trigonometry or aviation, navigation like sea navigation and all these type of things. What are these things? Well, let me draw the following. I'm drawing the ground and I'm placing an observer over here, a human observer who has eyes, obviously. And what these angles mean are the following. If you have an observer and if you trace a horizontal line through his or her sight. And by the way, by observer, I don't necessarily mean a person. I can put in here any other measuring device which can act as eyes. You see what I mean? So it doesn't really have to be the eyes of a person. So you have the horizontal traced through her or his eyes. And let's suppose that this person can look at a plane, or I don't know, at a cat on the floor. Okay, and when you trace from his or her eyes, I'm gonna go for her. When you trace from her eyes the line of sight from her eyes to the plane in this case, then this line of sight makes an angle with the horizontal. You see, this is the horizontal, this is the line of sight, la línea de visión, the line of sight, and this line of sight makes an angle with this horizontal, which is this angle. This is what is known as the angle of elevation. I'm just gonna write that. And the same goes, well, something similar goes when this person looks down. If you trace a line from her side or from her eyes to this cat, in this case, in this way, then you can see that the line of sight makes an angle with the horizontal, which is this angle in this case, and this is known as the angle of depression. So basically, in a nutshell, angle of elevation is when you elevate the angle or the line of sight above the horizontal, and the angle of depression, is made when you drop the line of sight below the horizontal. That's more or less what they mean. Okay, so we need these two things so that we can talk about the following problems. What do we mean by application of trigonometry? Well, solving some actual real problems that occur every now and then in life. For example, these type of things. I'm gonna be showing you 3 problems today and maybe another 4 or 5 problems throughout the week. So the first problem reads the following. A man is outside a building and is 30 meters from the base of it. So let's draw that right away. So we have the ground, we have a building, and we have a man which is outside of it and is 30 meters from the base of it. So let's place the man, let's place the man over here, okay? And this person is 30 meters from the base of the building. So this is 30 meters. Okay, what else do we have? The angle of elevation between this observer and the top of the building is 60 degrees. So the angle of elevation between this observer, between his eyes and the top of the building is 60 degrees. Now, since we can actually make in here let's say an accommodation or an assumption. I'm gonna say that the man is actually small enough in order not to consider this the technicalities of the problem. What I mean is this: technically speaking, I should draw the line of sight. I'm gonna do it in yellow. I should draw the line of sight from his very eyes, like from right there to the top of the building. This would be the correct diagram. But since usually the height of a man with respect to buildings, and maybe I should have added in here a tall building. Their sizes are so, you know, mm, they're so different in size. This is very much larger than the size of a man. We can say that basically we can consider the man as just a point in the ground, like just a particle, like that's your man basically. And so that the line of sight goes basically from the ground to the top of the building. We can make this assumption, and in this case it's not that bad. I should have added in here a very tall building in comparison to the man's height. Okay, with that assumption, then this angle is 60 degrees. With that assumption in mind. Okay then. So now guys, can we find the height of the building? Can we find this length, the height of the building? Well, let's see. We have created basically a triangle, which is this, as you can see, right? We know this side, by the way, this is a right triangle, so I must specify it. This is a right triangle. We have one of the sides of this right triangle. We have this angle and this other angle, and we're looking for this other cathetus. This is one of the cathetus, this is the other one. And basically we can use the trigonometric functions that we know of in order to calculate h, which is this little bit. Okay, what do? We know, for example, the tangent of any angle theta in relation to right triangles, is equal to opposite side over adjacent side. Okay, so I'm gonna use this definition in order to solve this problem, right? I can say the following: tangent of 60 degrees is equal to the opposite side, or the opposite cathetus, which is h, over the adjacent side, or the adjacent cathetus to the angle, which is 30 meters. And we have written this equation. And if I isolate h, I get 30 meters times the tangent of 60 degrees, and I'm done with the problem. Whether you actually calculate the height in decimals or you just leave it like this, it's pretty much the same. Well, it is in fact, I mean, for this type of problems, it's basically the same. This is the exact solution. Remember, I often tell you that this is the exact solution, and you can approximate your solution once you calculate tangent of 60 degrees in any calculator. Let me bring mine. So after you multiply 30 meters times the tangent of 60 degrees, let's see what you get. Okay, you get 51 meters, approximately 51.9 meters. This is the approximated answer. This is the exact answer, and this is just the approximated answer. Okay, I usually recommend writing both: the correct exact mathematical solution and the approximation. That's okay. So that's how you can use trigonometry in order to know the height of a building. You just displace yourself, like for example, you can be here, you can displace yourself a little bit from the base of the building in this direction, and then look at the top of the building, measuring this angle with some device. It could or it could not be that easy. Okay, I'm not saying that this is very simple. You can do that, and then you can get the height. Again, when you measure this angle, guys, if you have a measuring device for angles, that's actually quite easy. But since we're talking mathematics, we're not talking engineering. I'm not gonna go into the details of how to measure actually this angle. That's of no concern to us. That's more for engineering stuff. Okay, next problem. This one. It says a girl is at the edge of a cliff of 200 meters. So let's draw that right away. And by the way, don't ask me why a girl is on the edge of a cliff. That's just a problem, okay? So this is the cliff. And then as you know, you have the water in here. Let's draw the girl. Again, since the girl is, I mean, in comparison to the size or to the, in this case, the height of the cliff, the height of the girl is not that important. What I mean is the girl is very tiny in comparison with a cliff. I'm just gonna draw her as a point, okay? This is an assumption. This is an assumption that I'm making, which is valid in this case. If the cliff were not that big, then this assumption would be wrong, okay? It's like when you look at the distance and you see that a star is just, you know, when you look at, at the sky, you can see that a star just looks like this, right? You see? So from your perspective, which is very far away from that thing, you can say that this is a point. Okay? Now, is this really a point? No, of course not. If you get closer, that's not the case. But in your context, okay, when you look at the star from the Earth, they look as a point, and you can say, okay, the star is just a point, and I can proceed with some problems about stars and the location of stars, treating them as points. It's kind of a similar reasoning. The height of the cliff is so much larger than the size of the girl that we might as well consider her as just a point. You should be able to do these types of assumptions every now and then. Okay, so we have a girl at the edge of a cliff, not perhaps the best idea, but okay, let's continue. She sees a boat coming at an angle of depression of 30 degrees. So let's draw a boat coming towards the cliff, and the girl sees that boat at an angle of depression of 30 degrees. And remember, the angle of depression, guys, is the following angle. This is the horizontal, this is the girl is looking down, so this is your angle of depression. This is 30 degrees. Okay, fine. By the way, remember the cliff is 200 meters in height, so I'm gonna write down here 200 meters for this length. So this is 200 meters, this is 30 degrees, this is the line of sight, this is the boat, this is the water. What have we created? If you look at this shape, again, one more time, this is a right triangle. This is my right angle. And one more time, the distance, well, a similar question in this case. We have at what distance is the boat from the cliff? So basically, we want to find this distance. The distance from the boat to the base of the cliff. I'm going to call it x. Okay, so what do? We do trigonometry, and we help ourselves with the trigonometric functions of angles, of right triangles. If I know this angle of 30 degrees, then I can know this angle. Since all of this plus this should be 90, therefore this is 60 degrees, right? Okay, and therefore that's it. That's all we have to, that's all I can, that's all I need in order to get me x. Why? Because I have, this is 20 meters, this side, this angle is 60 degrees. And so with respect to this angle, I can use, one more time, the tangent of 60 degrees. Remember, that's equal to opposite side over adjacent side. And so the tangent of 60 degrees is equal to the opposite side, which is, if you look at this angle, the opposite side is x. So I just write it down, over the adjacent side to 60 degrees, which is 200 meters. Okay, and one more time, we can isolate x in order to get 200 meters times the tangent of 60 degrees. How much is that? That's going to be 200 times the tangent of 60. We're going to get 346.4 degrees meters. Now, I'm sorry, that's not degrees. We're talking about distance, right? Meters, approximately. Okay, so these are just two very classic problems in regards to trigonometry. I have this other problem which I want to talk with you, but live. Like I want to discuss this problem with you, and I want to ask you questions, etc. How can we measure the distance between two faraway points using a theodolite? I'm going to tell you what this means in a moment, or a laser, or any other device for measuring angles. We're going to see how this works, but I want to do it with you. So let's stop it right here, guys.